chapter. Cruising right along. So on Monday, we looked at the situations where we basically knew our standard deviation or we were able to calculate. So we knew it for the ones with the mean, and we were able to calculate it for the ones with the proportion. So first problem we're going to look at is basically just a quick review of that before we move into the other ones. So let's look at this one. So the biggest question out of it, because we have two different ways we can look at it. We're looking at the mean or we're looking at the proportion. So is this a mean problem or a proportion problem? You're always going to be able to tell in the question. Yeah, it says estimate the actual mean. It'll say estimate the proportion if it's a proportion problem. So like that's the clue that's going, okay, which direction am I going? So this is a mean problem. Not mean as in bad, just mean as in average. All right, so what do we need to know? We need to know our mean. What else?
But we have to find out.
Yeah. Well, what do I need to know to figure out the end? So what are the pieces I need for the formula? Was it sample size? Yeah. Standard deviation. And one more. Plus 50. I need to know my confidence level. So in this case, we're doing a 99% confidence, which gives me what as my Z? 2.575. Okay. All right. What was my formula? It was X plus or minus Z times standard deviation over the square root of n. All right, so find me my range. So what's the low end? Yep. And that's the high end. That's off.
5,036.42.
Yeah. You figure out what you did wrong?
Yep.
Okay. Normally it's just typing something in wrong. All right. Simple enough? Okay. Now we're going to think way back. How do I find my standard deviation? Yeah. Yeah, it's the square root of the variance. So, and how would I find my variance? That's when I have a proportion. But yes, that would be when I have a proportion. Yeah.
Are you talking about like their data?
Yeah.
Would it be like the number minus the
Yeah, it was that whole big long process, right? Key piece of information when we have the data. So in this problem, I gave you, we did a sample of 50 pieces of chain and we found the mean. But then it goes, well, based on past history, I know the standard deviation is 100 pounds. If I know my standard deviation is 100 pounds, to find the standard deviation, I need to know the mean, right? Because the first step in the standard deviation process is the value minus the mean. So I know the mean already for the entire population. So why do I have to do all this? If I already know the standard deviation for the population, I have to know the mean for the population. True? Okay. So in the vast majority of situations, you are not going to know the population standard deviation. Okay. We start off with these because they're simple and they're straightforward and they use the Z table and stuff like that. But in reality, you're not going to know that. So we have to have a process for when we only know the sample information. Okay, who wants to pass these out? Thank you.
Yeah.
So when we're looking at the bell curve, what was the number of data that I said, once you get this, we can always use the Z table or the Z and the normal curve? How many pieces of data? It has a 3 in it. It's actually not. It's actually a very small number. You're getting closer. It's 30. Well, I'm like, we're talking about thousands of data things and stuff like that. 30 is generally a small number. So as long as you have 30 points of data, we typically can assume it's normal and we don't have to go through a bigger process. So if I had less than that, we'd have to determine if it's a normal set of data, which most of the situations that I'm going to give you, you're going to be able to assume that. You're not going to have to figure that piece out. So, but it's not going to necessarily be exactly what that normal curve is. So you can see if I only had 3 pieces of data, we're at that red line there. And it's shaped like the bell curve, but it's not exactly. It's a little more spread, right? And then the green is when I have 14 pieces of data. It's getting closer to that curve. But again, it's not exactly if you look down the bottom. Okay. Oh, thank you. All right. So the T table is going to give me the values under this curve that are not specifically the normal curve. All right. The process that we're going to do is pretty much exactly the same. We're not going to really have to change much and how we're doing this. So let's look at this. Of course, it's going to give me a split problem. All right. You ever worked for a manager who goes, you should be able to complete this in this long. And if it takes you longer than that, something's wrong. Managers always like to do those things. It's like, I can finish it in 20 minutes. So if you don't finish it in 20 minutes, like, no, that's not the way the world works. But when we're going out and bidding on projects and stuff like that, we kind of have to have a general idea of how long things are going to take. Anybody know a mechanic like that works in an auto shop? So when you work in an auto shop, every job has a set amount of time. So brakes should take an hour, or a transmission change take 20 hours, things like that. That's what you charge the customer on that hour or that 20 hours. However, if you finish it in a half hour, do you charge the customer a half hour? Nope, you still charge them the hour. Okay, so as a mechanic, you want to work quickly. Yes.
The same thing with contracting, although contractors never get it done in time.
Well, yes, you always want to, but the difference between contractors and mechanics is the contractor, you're setting the time, where actually there's a book that they have at the auto shops that every job has this long to take. So this way, and it's always longer than it should take, but it's taking care of like if there's an issue and stuff like that in there. So you always want to finish it faster because you make more money that way. Yeah.
I guess a bit off topic, but what about with construction company? Because I know because both of my parents work in construction, so they have to bid and they have like a general.
They have a general idea of what it's going to take. And normally it's based on what they've done in the past. So like, I don't think there's a set standard on like how long a set of stairs is going to take. Like, I don't think there's a set, like there might be a standard for it. I'm going to guess no, because that's typically how most places will underdo their bids, because they'll set the time a little low. They're going to get it done a little faster and stuff like that. So they can play with those numbers a little bit. So, but that's the thing. It's like, you always want to finish faster than what you should, because then you make more money. The key is you want to make the more money and not your company make the more money. So, all right. So in this case, a manufacturing company is interested in the amount of time it takes to complete a certain stage of the production process. So they're trying to figure out how to optimize their production line. So they've taken 10 samples. Okay. So in this case, N is what? We've taken 10 samples. So that is my N. Okay. So things aren't changing. We're still using the same process. I'm going to show you where the T table comes in a minute. The average completion time is 23.45 minutes. So that is your what? That's my mean. With a sample standard deviation of 4.32 minutes. That's the key piece of information here. It's sample standard deviation. Okay? It's not the population standard deviation. So typically we use an S to show that instead of that squiggly little O. So that's 4.32. So if they give you your population, we use the Z table and what we were doing on Monday. If they give you your sample, we have to do it with the table that you just got handed out, the T table. I will show you a nice little thing later about the T table that's going to help you, so you don't have to necessarily need both the T table and the Z table, because all the information you need for Z is on here as well. All right. What was the other piece of information I need to know? I needed to know my critical level, or the confidence level. In this case, it's what? 95%. Now, that is where we don't know what we're looking at yet. Okay, I can't go back to the table for my z's because I'm not using the z. Okay, I'm going to be using this new table that I got. All right, so the first thing we need to find, so we're using what's known as, it's going to be a t, not a z. So let's look at the t table. Let me actually pull one up. I think this is the San Jose one. Yes. Good. All right. So if we look at this table, there's some pieces of information that we want to use or that we want to look at. The first is the top. Okay. The top's got 3 lines of information. It's got the cumulative probability, it's got the one-tailed, and it's got the two-tailed. All right. Right now, since we're looking at confidence intervals, we are always looking at two tails. We're looking at both directions. Okay. Next week, we'll talk about the one-tailed stuff. So right now, we're looking at the two tails. So where would the 95% be in two tails? Which one of those do you think I'm going to use for two tails? For 95%? Because I don't have a 95% there. The numbers that they gave you are the opposites. So the numbers that they gave you there are 1 minus it. So what's 95% represent? The 0.05. Okay, so we're looking at that. Okay, everybody get that point? Understand that? Yes? Because that's one of the two major pieces of information you need to know. The second piece of information we need is the other column, the degrees. This is known as degrees of freedom. Okay. So degrees of freedom is always n minus 1. Okay, so my degrees of freedom is always going to be n minus 1. All right, and that's what these numbers over here is. If you look down the list, you have every single number up to what number? No. On the degrees of freedom list, on the side. You have all the numbers, every single number goes 1 through 30. And then after 30, it kind of jumps, right? They did 30, 40, 60, 80, 100, 1,000. What was the number I told you was the important number? 30. Okay, after 30, it's basically the Z. And you can see it gets really close to that Z down the bottom. So the vast majority of the ones that we're going to look at in this situation fall between that 1 and that 30. So what is my degree of freedom for this problem? It's going to be 9 because it's 10 minus 1, which is 9. So on this table, we're looking at the degrees of freedom of 9. And we're looking at 0.05 for the column in the two tails. All right, so what's the number when you go 9 all the way over to the 0.05 for the two tails? Make sure you're looking at the two tails and not the one tail.
And then what?
The 0.05 in the two tails. And that's my T. You looked at the one tail for the 0.5. So we're looking at hold on, I can do this and put it on the screen so I can actually copy and color it. So we're looking in this row, and then we're looking at that. So we're looking at that row. So that ends up being that column, the number I want. Because I want a 0.05 in the two tails and with a 9 degree of freedom. So unlike the Z table where all the numbers in the middle were the probabilities, this is actually, these are basically all your Z values. They're giving you the value of that piece. Okay. That's the main difference between these two tables. So the T table is never going to give you a probability at that point. It's going to give you a number, and then we're going to do something with that. Okay. Does that make sense to find that? All right. The nice thing is, now my formula is basically the same as I did before. What was the formula before? Mean plus or minus what? Z, but now we're going to use T times.
The sample standard.
So it's a standard deviation over the square root of it. Okay. Everything else, in essence, the formula is identical. The only difference is how you're going to find that T. Okay. So your formula, same setup. It's just the Z changes to a T. So I have 23.45 plus or minus 2.262 times 4.32 over the square root of 10. What was it? 23.45, 2.262. And there's your plus or minus. And you actually, if you do your formula in Desmos and use the Z, and when you type in your formula, like we were doing on Monday's class, you can leave it there. You don't have to change it. Just put the number for T in that spot because the formula didn't change. So you can see how I just left the formula there, and I just plugged in my t for that z spot. Because everything else, it's the same formula. Does that make sense? Or no? We're going to do a couple more, don't worry. All right. Okay, what pieces did it give me? Oh, okay. Which pieces did it give me? Is what? So my sample size is 15. And with my sample size, I can find my what? You can find my degrees of freedom, which we'll do that in a minute. What else did it give me? The what? What's the mean? Okay. What else did it give me? Standard deviation, the sample standard deviation, right? So that's 1.4. And what confidence interval am I doing? 95%. Okay. Good. Find me my T. All right, what's the T? I already got it? That's correct. 2.145. My degrees of freedom was 14. And I'm looking at the two-tailed .0. So think about when we're looking at the bell curve, right? If I want both sides, two-tailed. Since we're looking at a confidence interval, we're going from the center out, we're looking both sides. Next week, there will be situations where we'll only want to look at one side. And that's where the one-tailed comes in. No, that's still two-tailed. Because it's going both directions. If you're between something, you're going both ways. So pretty much up to this point, everything we've looked at has been, like when we're looking at the z-score and everything else, has all been two-tailed. When we were doing the percentages, if it was just greater than or just less than, those type of situations, those were the one-tailed when you're looking at one direction. And that's what we're going to look at in chapter 11 is we're going to take both of those two things and put them together. All right. So we got everything we need, right? So now just plug it into the formula. All right. Let's do. Let's confuse you. That sounds good. All right. Okay. Find me my confidence interval. Yes.
Are you asking us to tell you what find out?
Huh?
Are you asking us to tell you what it is? Find out.
Well, when you get it, tell me what it is. It's going to be a few steps. There's no way you have it yet. What's the? No.
But it's you.
Yes. All right. So we've got a mean of 9.75, a standard deviation of 1.12. Our number is our sample size is 61, which gives degree of freedom of 60. And we're looking for 80%, which goes to 0.2 on the two tail. So T is 1.296. By 1.2. One, two. That's what you should have gotten for your 2. That makes sense? Are we able to find the t fine? Are we getting better at plugging in the formula? All right, do this one.
I originally thought that the N was going to be 6, but then the machine was swapped to
Okay.
12.
Uranus 36, that's correct. Yeah, that's 36. What's this problem give you? Gives me the mean. Sample size. What else? Huh? Gives me the confidence level. Okay. What else does the problem give me? Which standard deviation? Population. Which means we use Z. Population standard deviation. We're using Z. Now, look at the very bottom of the T table. What's it got in the very bottom of the T table? It's got Z. Look above 95%. 1.96. So you don't have to go back and look at your other table for your Z's. They're on the bottom of the T table. Okay. The key is which standard deviation do they give you? So you asked, 36 isn't on there. There was a reason. We were looking at the population, so we didn't care about the degrees of freedom. Okay. If it was sample, degrees of freedom, we need to look at the T's. Population, I need to do the Z's. Okay. I told you, I said, let's confuse you. But that's going to be the hardest part of the test. That's going to be the hardest part of your homework and everything else. It's not, it's English, right? Remember, go back to that. It's all about reading what they're giving you. The calculations and stuff, simple. It's the same thing no matter what, basically. It's just a matter of how you're finding that piece. But if you don't read that step correctly, and you're now doing a degrees of freedom and everything else, you're going to get the wrong answer. So you have to make sure you're looking at which standard deviation it's giving you. Population is Z, sample is T. Okay? Those are the two things you're going to be looking at. So in this case, it's Z. And like I said, I would type the formula once in the Desmos and just leave it there. Like, you don't have to keep constantly changing it. What's my standard deviation? 4,400. I did 36. So there's the two ends. All right, do this one. What'd they give me? Yeah.
The N would be 500.
Okay, so I've got N, got my sample size.
That would be 20 over 500.
Okay, so in this one, do they give me a mean? No. Do they give me a standard deviation? No. So what are we looking at? It's a proportion, which means we have to calculate those two. So P hat is the 220 over 500, which is 0.44. And how do I calculate the standard deviation? Over N and the square root of that. Oh, yeah, and it's 500. Like, why did I put the N there? So I got 0.0222. What is my Z? So in this case, in proportion, you're always using Z because you always know your standard deviation because we can find it. How did you get that? That's not a Z. Remember, the Z score you're just looking at is based on the percentage. So the 95%. I know. You had the Z, you're looking for the, yeah. So 95% for Z is what? 1.96. If this is one of those little tricks that you don't have to keep typing in your formulas a million times, remember that because in this one I divided by the square root of n already, I don't have to divide by the square root of n in my formula, right? Since I don't want to have to keep dealing with this, what's the square root of 1? 1. You can just make that n1 in your formula, and it basically eliminates that, so you don't have to retype it back in. Don't put in the 500 because that's going to screw your formula up. But if you put 1 in there, it won't screw it up. Makes life a little bit easier. Just little things to help use your time effectively. So the actual proportion somewhere between 0.396 and 0.484. They have vet classes here now. That's what, yeah, that's what it is. That's why there's always a dog next door.
Can we just play
I keep getting told that my girlfriend is there. So you should bring Waldo. You should bring Leave. No, I can't bring my dogs to class. I have a dog called Waldo. Yes, I do have two corgis. Yeah. Where's Waldo? We call him Buggy a lot, but yeah, his actual name is Waldo. All right. What about this problem? How do I do it?
So at the end, have
Yes.
to start. We're-
Guys. Hold on, I'm gonna I'll erase this so I can have some room in there. So n is 10. Yes.
Yes. And the average is 7,180. The mean is 7,180.
All right. So this is one of those problems that's designed to mess you up. Because they got a whole bunch of stuff in here. All right. So the nation's 19,000 funeral homes taken 13 billion a year. The average cost of funeral being $7,181 in 2014. Suppose that the cost of 10 random funerals taking place in an affluent suburb of Pennsylvania are given below. You're asked to construct a 90% confidence interval for the average funeral cost in the suburb, not nationwide. So we are not using the 7181. We need to find the mean and the standard deviation for the sample they gave us.
To add them all up and then divide them.
So, but remember, we have a calculator that can do that for us. So remember back when we did standard deviation, we have a calculator for it. So all we do is type those numbers in. Let's see if I can copy and paste them from here. Nope, I cannot. All right, fine. So 8206. 18. These are cheap. Funerals are a lot more expensive than this now. What? The funerals are so much more expensive now? I know.
Oh, in Europe, you have to actually rent a plot. And if you don't pay your rent, you'll actually clean your body. Yeah.
All right, so we've got the data put in here. Is this a population or a sample? Sample, so make sure you click sample. All right, so I've got my standard deviation, and the nice thing is it also gives you your mean. So I don't necessarily need to find the mean because it'll do that for me at the same time. All right. Oh yeah, it actually shows you up the whole process. All right. So we've got that. We don't need the sum. Okay. So so am I using Z or T? Why? Good. All right. So what's going to be my T for this one? So what am I using for my yeah? Yep. So my degrees of freedom is 9, and I'm looking at the 0.10 two-tailed. All right, so now just plug those numbers in. What's my mean? 51.5. 178355. Oh, put that in the wrong spot. All right, so you've got those two numbers. All right, so can you make the claim that the costs of funerals in this affluent suburb are more expensive than the national average? Why? Yes.
That's the thing, is that, I mean, yes, it can be, but for the most part, like 99% of the time, it's going to be more. It's only less than, like, on the low end, the average is only less than like 100, is only less than $100.
Okay. Everybody agree with that? All right. The answer is no.
All right, no.
So there, okay. And here's the reason why I like this problem. And this is actually going to lead us into what we're going to be doing next week anyway. What is my confidence interval telling me? It's saying I am 90% confident that my mean is somewhere between 7017 and 9085. Okay. It's not saying the mean is in that entire range. It's saying I'm 90% confident. The mean is only one number. All right. The mean is only one number. It's whatever that is. I don't know. I got my mean of my sample was 8051. Based on that and the information we've got, I know my actual mean, if I looked at them all, should be somewhere, or I'm 90% confident that it's somewhere between 70.17 and 90.85. Since it goes below the national average of 7181, I would have to say, no, I cannot make that claim because it could be lower than that. Okay. That's the difference. I'm 90% confident that it's somewhere between here, and that means So I'm 90% confident that it could technically be less. Okay. When we start to make those claims, that's the most important part about the confidence interval is that we're saying that the mean is somewhere in there. I don't know exactly where it is. Okay, but the mean is still only one number. So that's not a range saying this is the range of all possible values I can get. It's saying the mean is somewhere in here. It's just a matter of where. And that I don't know because I can't get an exact number. To get an exact number, I'd have to get a lot more data, and that would get a lot closer. But with the data that I have, this is as much as I can make that claim. Okay. Next week with chapter 11, we're going to go into what's known as hypothesis testing, which is exactly what we just did. It's like when we get information, we're then going to be able to start making a claim about is what I decided at the beginning true or false. Okay, can I make this claim or can I not make this claim? All right, you should be able to finish chapter 10 now. We have one more week left of class, basically.